Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in as we go through everything you need to know for next week's test, and it will cover similarity and similar triangles. No congruent triangles. That was just us linking back similarity to something you'd already learned. So let's first look at how you actually create a similar figure. So let's just draw like a triangle. So what I'm going to do is I'm going to enlarge this triangle with scale factor 3. So we need to enlarge it about a point called the center of enlargement. So this is what you do. You draw a line from the point to each vertex of the shape. And what we're going to do is we're essentially going to move each vertex so it's 3 times further away from the point than it was originally. So we need to measure the distance of each line. So this one here was 2.5 centimeters and this was 6 and 4.7, okay? I know it might look a bit different depending on the size of your screen. So what we're gonna do is we're basically gonna move each vertex so it's 3 times further away from point A. So let's look at this bottom vertex here, 2.5. centimeters away. So what we want to do is we want to make it so it's 7.5 centimeters away. Now we want the new triangle that we create to have the same angle. So we need to keep going along the red line. So it needs to be 7.5 centimeters away along that line. So I continue the original line for another 5 centimeters. So the total length of this line is now 7.5, 2.5 plus 5. So it's 3 times larger than it was originally. Now I apologize, I can't use rulers on my iPad here, but yours I'm sure will look beautiful. So basically we moved this vertex here. So we should label the vertices. So I'll call that vertex B. And then we call this B dash, the image of B. Now we're gonna do the same for the next vertex. So I'll call that C and this D. So we'll move vertex C. So it was 6 centimeters away from the center of enlargement originally. So now we need to keep going along that line for a further 12 centimeters. So that moves the vertex all the way over there. So from here to here was 12 centimeters. And then we call that C dash, the image of C. Now we're going to do the same to the last vertex. So I'm gonna need to continue the line from A to D, and then I'm gonna have to continue it for 9.4 centimeters more. And so that vertex will end up here at D dash. And as I said, this length here, from here to here was 9.4, okay? Again, I apologize because my iPad doesn't allow me to use rulers. So then when you've got moved all the vertices, all you have to do is join them up, easy as. So our new triangle will look like this. Now because what we've done is we've moved each vertex so it's 3 times further from the original point, each of these side lengths will be 3 times its corresponding side. So this side here, D dash C dash, will be 3 times DC. Because we kept going along the same line, that ensures that the two triangles will have the same angle. So what we've done is we've created 2 similar triangles here with scale factor 3. The larger triangle is the same shape as the smaller triangle, except its sides are just 3 times as large and it has all the same angles. So that's how you use the center of enlargement to create a similar shape. So you can create similar triangles, quadrilaterals, or whatever. So now we're going to look at a more formal definition of similarity. So please pause and copy this down if you need. Okay, so we say that 2 shapes are similar if pairs of corresponding angles are equal and pairs of corresponding sides are in the same proportion. So with congruence, the 2 shapes were congruent if one shape was just a reflection, rotation, or translation of the other. Here, the 2 shapes are similar if one of the shapes is an enlargement or a dilation of the other shape. So these 2 conditions must both be true for 2 shapes to be similar. When we're not talking about triangles, we're talking about quadrilaterals, pentagons, and higher polygons, These two statements aren't equivalent, meaning it's possible that one of them is true and the other is not. So I'll give you an example of that. So let's say I have these two quadrilaterals here. Obviously the first is a rectangle, the second is a square. Now clearly the first condition here is satisfied. Pairs of corresponding angles are equal, right? But the sides are not in the same proportion. This side, which corresponds to this one, 4/3, that's the proportion there. But this side and its corresponding side, the proportion there is 2/3. 4/3 does not equal 2/3. So therefore, the corresponding sides are not in the same proportion. That second condition basically means that if you take the first shape, you multiply each side by the same number to get the corresponding side in the other shape. We didn't do that here. We don't multiply 2 by the same number to get 3, as we do to get from 4 to 3. We need to multiply this side by a different number to get its corresponding side, then this side to get to its corresponding side. So these two shapes are not similar, even though pairs of corresponding angles are equal. The opposite can be true as well. So let's say I'm just going to draw this shape here. Again, apologize for my bad drawing. This is supposed to be a parallelogram. So in any parallelogram, we have opposite sides that are equal. So if this was like 12 and this was 10, we'd have opposite sides being equal to each other, okay? So then I'll draw a rectangle and I'll make it 6x5. So here, corresponding sides are in proportion because 12/6 does equal 10/5. In other words, I need to to get from this shape to this shape, I take each side and multiply by 2 to get the corresponding side in the bigger shape. So the second condition is true, but the first one is clearly not. Pairs of corresponding angles are not equal in this case. So this angle and this angle won't be equal because this one is not a right angle. So these won't be similar either. So I'm doing all this to show you the two shapes need to be similar if both of those are true. Corresponding angles must be equal and pairs of corresponding sides in the same proportion. If we know that two shapes are similar, we can use that to find unknown sides and angles. And that's what I'll show you now. So again, please pause and copy down if you need. Okay, so in this question, I'm giving you two quadrilaterals, two trapeziums. I'm telling you they're similar, and we can use that to find the value of x and find the value of y. So I've marked all the pairs of corresponding equal angles just to make it easier to determine which side corresponds to which. So because these shapes are similar, I know that all sides will be in proportion. So I can use that to easily find x and y. So the first thing we do is find the scale factor. So the scale factor is how many times larger the sides in the bigger shape are than the smaller shape. In other words, it's what you need to multiply each side in the smaller shape by to get the side lengths in the larger shape. So what you do is whenever you're trying to find an unknown side, I suggest you always do larger shape divided by corresponding side in the smaller shape. That just makes things a little easier, because if you do it that way, when you're trying to find unknown sides, you always times by the scale factor to get a side in the larger shape, and you always divide by the scale factor to get a side in the smaller shape, okay? So scale factor here is 2.5. That means each side in the larger shape is 2.5 times as big as its corresponding side in the smaller shape. So let's use that to find x. So x is in the larger shape, so we take its corresponding side. Because it's in the larger shape, we multiply by the scale factor. So x will be 8 times 2.5, which is 20. Now to find y, that's in the smaller shape, so we take corresponding side and divide by the scale factor. So x would be 20 and y would be 10. How easy was that? So we've looked at similar figures. Any two polygons can be similar, but we're going to focus our attention now on triangles. So again, please pause and copy down if you need this. So now we look at similar triangles. So I said before, two shapes are similar if all angles are equal, pairs of corresponding angles are equal, and pairs of corresponding sides are in the same proportion. So it's pretty similar to congruent triangles, except the sides aren't equal, they're in proportion. But triangles are a little easier. I showed you before, for those two conditions, sometimes shapes satisfy one but not the other. Sometimes the pairs of corresponding angles are equal, but pairs of corresponding sides are not in the same proportion. Fortunately, that never happens for similar triangles. So we can do things a little easier, and there are 4 tests for similarity. So SSS means that all 3 sides are in the same proportion. AAA means that all pairs of corresponding angles are equal, and then we have SAS, remember it must be 2 sides and the angle between them, and RHS. So they're very similar tests to the ones you used for congruence. So the reason we can use this test is that we don't have a situation where one condition holds and the other fails. So in triangles, if pairs of corresponding sides are in the same proportion, then pairs of corresponding angles will be equal. If pairs of corresponding angles are equal, then pairs of corresponding sides will be in the same proportion. So you don't need to test every side and every angle in triangles because they're a little simpler. Okay, so let's look at some examples. So in this diagram, we have 2 pairs of sides and a pair of angles. So 21 over 14 does equal 18 over 12. Both of them equal 1.5. So this pair of corresponding sides and this pair of corresponding sides are in the same proportion. There's a consistent scale factor, if you like. And we're told that this angle and this angle are equal. So these 2 blue triangles are similar by the SAS test. 2 sides in proportion and the angle between them is equal. Let's look at another example. Okay, so these 2 triangles here, are they similar? Well, we only have information about side lengths, not angles, so if we use a test, it'd have to be the SSS test. Now you might be thinking, oh, but 16 over 7 doesn't equal 14 over 8. But that's not right because they're not corresponding sides. So I could flip this triangle, I could flip it kind of that way to get on top of this triangle here. So these 2 are similar because 16 over 8 equals 14 over 7 equals 10 over 5. So line them up, so shorter side corresponds to shorter side, middle side corresponds to middle side, and largest side corresponds to larger side, okay? So in all these cases, 16 over 8, 14 over 7, 10 over 5, all equal 2. So these 2 triangles are similar by the SSS test, okay? Fantastic. Now we're going to look at actually proving that 2 triangles are similar. So again, please pause and copy down if you need. So on the last slide, we just went through which tests show that 2 triangles are similar. Sometimes you will be asked which test shows they're similar, and you can just write the test. But if you're asked to prove that 2 triangles are similar, you need to go through and say which angle is equal to which angle and give a reason, or which sides are in proportion and give a reason. You have to have some reasoning why they are similar. So that's what I'm going to show you now. Whenever you're asked to prove something, you need a few lines at least. So I'm going to prove that the top smaller triangle is similar to the larger bottom triangle. Now the piece of advice I'll give you, whenever you are given 2 triangles, you need to determine whether they're similar or prove that they're similar. If you don't have information about side lengths, it must be AAA. So I know in this diagram, I'm going to have to find pairs of equal angles. So I know that this angle and this angle are equal because they're vertically opposite. So I will write that formally. So angle ACB, which is this angle here, is equal to that angle there, which is angle DCE. Okay, we must give a reason for it. So I'm just going to abbreviate it. Vertically opposite angles are equal. Now, because this line AB is parallel to DE, that means that these two angles will be equal because they're alternate. So I write that angle BAC equals angle CED, and the reason is alternate. Now, the AAA test is pretty much the same as the AA test. So what I mean by that is, if you have two triangles and you show that there are two pairs of equal angles, then there must be three pairs of equal angles. So this angle and this angle must be equal because angles in a triangle add to 180 degrees all the time. Okay, so once you've shown that there are two pairs of equal angles, you're done. So I have shown, therefore, that triangle ABC is similar to triangle EDC, and I've used the AAA test, or AA. Okay, so two pairs of equal angles means that they're similar. So when you're writing this similarity statement, you've got to make sure that the vertices line up. So vertex A corresponds to vertex E. That's where the equal angles are. So I wrote A first in the first triangle after I wrote E first in the second triangle. B corresponds to D because they have the same angle there, so I wrote B second, D second, and C corresponds to itself. So that's done. I've actually proved that these two triangles are similar, okay? Now we're just going to look at a few harder questions. So again, please pause and copy down if you need. Okay, so we'll do this question's a little harder where we're finding the value of an unknown side. So firstly, if we look at the two triangles, so we've got this one here and the big one there, we can really only find x if we know that they're similar. So they turn out to be similar. This angle's common, and then these two angles are corresponding. Once you have two pairs of equal angles, then you must have three pairs of equal angles. So this angle and this angle must be equal. So the two triangles are equal by the AAA test. So the scale factor here is not 9/6, because this whole distance here is 15. That's the length in the large triangle. 6 and x are not lengths inside a triangle. So the scale factor, larger side divided by shorter side. So it's 15/9, or if you want to simplify it, 5/3. So then we need to find x. So this whole length here is 8 plus whatever x is. We don't know that. What we do know is that this length is 5/3 times that length. So 8 plus x equals 5/3 times the shorter side. Scale factor times the shorter side, okay? So 5/3 times 8, we just get 40/3, and then it's just like a normal equation. We subtract 8 from both sides, we get x equals 16/3, or 5.3 recurring. How easy is that? So the last thing I'm going to do is show you a worded problem involving similar triangles. Finally, we will attempt this question here. Building casts a shadow 24 meters long at the same time of day and in the same location. Person 1.8 meters tall casts a 2.7 meter shadow. Now we can actually use similar triangles to find the height of the building. So we'll just draw first off the person who's 1.8 meters tall. He casts a shadow that is 2.7 meters, okay? So then, of course, the sun would be like up here, and we can make this into a triangle. Okay, now we'll do the same for the building. So the shadow of the building is 24 meters long. We want to find how tall is the building, and we'd have the sun like up there. Okay, so if we're talking about the same time of day in the same location, the angle that the sun makes with the object, with the building or the person, will be the same. So what I'm saying is this angle here and this angle here will be equal, okay? And I guess I've just assumed here, but buildings, you know, they're always at right angles to the ground, and the person standing up 1.8 meters tall, right angle as well. So these two triangles are similar because they have two pairs of equal angles, therefore they will have three pairs of equal angles. Now that we know that we have some similar triangles, we can use that to find the unknown side here, x, and that's actually very simple. So the scale factor here would just be side in the larger triangle divided by the side in the smaller triangle. And then I just times that by 1.8. I times because I'm finding a side in the larger triangle, and that just gives me, that gives me 16. So therefore, the height of the building is 16 meters. All right, I hope you've got something out of this. Sorry for the long video. This has been the luckiest maths teacher in the world. Have a great day.